Hello everyone, my name is Mark Buckner, and in this video I'm going to demonstrate what I consider to be the easiest way to convert between the decimal numbering system and the binary numbering system. First, let's talk just a little bit about the difference in these two numbering systems. The decimal numbering system is our standard numbering system, and it is also called base 10. It has available to us the values between 0 and 9. The binary numbering system is also called base 2. The base 2 numbering system only has two values available, 0, of course, and 1. And the foundations of digital computing are, of course, zeros and ones. The machine coding language is zeros and ones. You can think of 0 as no electricity flowing. You can think of 1 as electricity flowing. You can think of 0 as false. You can think of 1 as true. You can also think of 0 as off and 1 as on. And in this video, we're going to take a series of numbers, both in decimal and binary, and convert between them. Okay, let me erase what I just did, and let's start. First step to converting between decimal and binary is to write out 8 values, and I'm going to try to make them large. I think I'll start about right here, and those values are starting with 128, 64, 32, 16, 8, 4, 2, and 1. In these videos, I am going to be focusing on 8-bit values, and let me get my cursor off the screen there, apologies. 8-bit values, or 8-bit numbers if you prefer. An 8-bit, you can also consider that as 1 byte, because 8 bits make up a byte. A byte can represent most characters, if not all, on the keyboard, at least the English keyboard, both uppercase, lowercase, digits, and several others as well. And when you're working with 8-bit values, you have available to you 256 numbers, or 0 between 255. Because if you count up all the digits between 0 and 255, you do indeed get 256. Now, you normally don't have to worry about converting between decimal and binary beyond this, mostly because there are several things in computing that are 8-bit in nature. Perfect example, of course, are IP addresses, which, for example, 192.168.0.0, for example, is a classic Class C IP, private IP address. And these 4 octets, and by octets I'm referring to these 4 values, can be between 0 and 255, for example. So in these videos, we are going to be focusing on 8-bit values, or 8-bit numbers for both decimal and binary. So let me get rid of this really quickly. Alright, let's begin. And I wrote a program before recording this video. I'm not a mathematician. My background is in computer science and information technology. So I wrote a program to convert between binary all the way through hexadecimal back and forth. So I randomly created a 100 values, numbers, and its equivalency in binary between 255, so I can make sure that once I do the calculation, what I have provided you is correct. I found out last fall in one of my classes teaching students how to do this. Doing math in my head and on the fly is not my strong suit. So hopefully I won't have any problems this time. Let's see. Let's do a quick example, and let's start with converting decimal numbers to binary. I'm just going to pick one from my 100 list here, and I'm going to start with, hopefully it's not too bad, 156. Oh, I don't know if I want to do 150. Well, we'll do 156, and hopefully I won't embarrass myself. So 100. Oh, apologies. 156 base 10, and this is pretty common means of showing that the numbering system for this value is indeed decimal or base 10. Okay, here's how you do this the easy way. We take these values and we determine whether or not these values are less than this value, our starting value. So you just got to ask yourself a series of questions. Is 128 less than 156? If it is, remember a moment ago I mentioned that you can think of 0 as off and 1 as on? Then, for example, because 128 is indeed less than 156, this bit location is turned on, or it gets a 1. So now we take 128 and subtract that value from 156. And you guys will have to bear with me. I learned how to do mathematics in the 80s, so this may not look like how it looks today. So I've got to borrow here, and this becomes 16. 16 minus 8 is just 8, I hope. And 14 minus 12 is 2. So, is 64 less than 28? And of course the answer is no. So this bit location is turned off. Is 32 less than 28? Again, no. This bit location is turned off. Is 16 less than 28? Of course it is. Oh, I forgot to turn it on. Remember, 1 is on, 0 is off. And we'll subtract 16. I believe that leaves 12, I hope. Is 8 less than 12? It is indeed. That gets turned on. With 4 left over. And with 4, we have ran out of value, in which case 2 and 1 are just 0. So if I did my mathematics correctly, then 156 base 10 is equal to 1, 0, 0, 1, 1, 1, 0, 0, base 2. And I'm going to look over at my, let's see, this is 156, and on my program it returned 100111100, so it does look like I did that calculation correctly. So this is the first one. 156 base 10 is equal to the equivalency in binary 100111000, using what I consider to be the easiest method. There is another method, of course, that I'll talk about in a future video of converting between binary and decimal. Okay, I'm going to use my mouse to erase this for a moment. And we're going to do some more and talk a little bit more about this. I am, just so you guys know, the equipment that I'm using here, I'm using a Windows 11 virtual machine. Whenever I record videos, I always use a virtual machine because my desktop on my host computer is chaotic. let's get rid of this as well. This application is called Microsoft Whiteboard. I'm not sure if it's the best application for this purpose, but it's what I was able to find. Okay. And the drawing tablet that I'm using is a very budget drawing tablet called from a company called XP Pen Deco 01V3 drawing tablet. Of course, I'm not using it for drawing. Okay. First, you might be wondering where these numbers come from. These numbers, because we are using binary, come from the numbering system to a starting power of 0. 2 to the 0 is 1. 2 to the first is 2. 2 to the second is 4. 2 to the third is 8. 2 to the fourth is, it's like 24. Apologies, let me try to make that better. 2 to the fourth is 16, so 2 times 2 times 2 times 2. 2 to the fifth is 32. 2 to the sixth is 64, and finally 2 to the seventh is where we get these values. Just FYI. Okay, let's do a couple more. Let's do a lower number. Let's try 23 base 10. So, oh dear. Let's see if I can do that better. I'm going to draw a line here so I can always erase below it. And I can do a couple and leave them up. So 23 base 10 equals, well, is 128 less than 23? No. Neither is 64 or 32. However, 16 is indeed less than 32. Oh dear. I don't know why I have to visualize this, guys. I'm not good at doing math. Well, it's 7. Yeah, 7, because 6 plus 6 is 12. 7. And that's all that's left over. Is 8 less than 7? It is not. However, 4 is. Of course, that leaves 3, and 2 and 1 is 3, so I'm going to have to turn this one on. And the 2 to the 0th position as well. And that clears us out. So, 23 in base 10 equals 0001011 in base 2, or binary. And that does look like the value that I got from my application. So, how can I test without having to write a program or go look at an online application, or worse, a generative AI prompt to make sure that I've got this correct? In a moment, we're going to talk about how to go between binary back to decimal, which is also quite easy, but you can also use that same strategy to check whether or not your results are correct. So for example, for every bit position that is turned on, we add the value of that bit position back, and when we total that up, it should equal the decimal value. So these three, 128 or 2 to the 7, 2 to the 6, 2 to the 5th are turned off, but 2 to the 4th is turned on. So 16. 2 to the 3rd is turned off, 2 to the 2nd is turned on. So 4 to the 1st and 2 to the 0th are also turned on. We add these up. 4 plus 6 is 10. 2 plus 1 is 3. Oh, sorry, I clicked the button. Is 3. That gives us 13. Carry the 1, and we add those two together to get 23. And indeed, we did do our calculation correctly. Oh, I thought that might erase. I apologize. I'm not super familiar with this tablet yet. I'm sure I'll get better using it. Okay, let's do another value. Let's do. Oh, I worry about this one. 177. Oh, just really quickly, by the way, in this number, you actually don't have to specify the trailing, or rather the leading zeros. If you just wrote this as, for example, 23 base 10 is equal to 1, 0, 1, 1, 1 base 2. You don't actually need to specify the trailing zeros. It always is assumed that these values start at the right and not the left. Okay. I think I said I was going to do 177 base 10. Is 177, or rather is 128 less than 177? The answer is yes. Why didn't I do 178? Okay, so this becomes 16, this becomes 17, and I believe 9 plus 8 is indeed 17. So 9 and I believe 4. Is 64 less than 49? It is not, so that's turned off. 32 is, so that's going to be turned on. Leaving 17. Is 16 less than 17? Leaving 1. So 8's position, 4 is turned off, 2's turned off, and then of course the 1 will wipe us out. So 177 on my application, it came back to 10110001, and that does look to be right. Okay. Alright, we'll do one more and then we'll switch to rather binary to decimal. 70. Well, I've done I did lots of 7s. Let's do something that's not has a 7 in it. 68. I don't have that one listed. There's another one that's 67. There's 70. Let's do 44. Why not? 44. Okay. Let me switch back. Alright, so 44 base 10 is equal to, well, again, for mathematic purposes. Eventually, of course, you won't have to do the mathematics. You'll be able to do these in your head. 128 is not less than 44, neither is 64. Those are turned off. 32 is. That's going to leave us with 12. 16 is not. That gets turned off. 8 is. And with us getting that bit position, we have ran out of values. So 48 base 10 is either 00101100, or you can eliminate these and just write 101100. 44, where are you on my list? 61. 101100 is what I have. Perfect. So that is converting decimal to binary using an easy-ish method. All right. Now let's do some binary to decimal. dokie. Let's scroll down to the bottom. Okay. I'm just going to pick one, or actually I'm going to pick a couple here at random. Okay, let's do 1, 1, 1, 1, 1, 0, 0, 1. Let's do 0, 1, 0, 0, 1, 1, 1, 0, base 2, 0, 0, 1, 1, 1, 0, 1, 1, base 2. Okay, we have 3 binary numbers here. The interesting thing about this top one, you may be able to figure it out without doing any difficult mathematics because everything is turned on except 4 and 2. So what's 255 minus 6? It should be the answer. But we'll do it the hard way, or I should say we'll do it out. Okay, so I'm focusing on this first one. And we'll see what this is in base 10 in just a second. So again, for the bits that are turned on, we add up its positional value, starting with 128, then 64, 32 is turned on, 16 and 8 are turned on, and then finally 1. And if we add all of these values together, and I like to group 6 and 4 is 10, 8 and 2 are 10, 8 and 9, I'm sorry, 8 and 1 rather are 9, and that gives me 29. Looks good so far, because it should be 249. 6, 7, 8, we have 10 there, 13, 14. We carry the 1, and indeed 249 base 10 is equal to 1111001 in binary. Okay. Let's do the next one. Alright, same thing. And we're going to be doing this one. So the 128th, or 2 to the 7th, I should say, position is turned off, so we won't write that down, but we will write 64. 32 and 16 are off. 8 is on, or 2 to the 3rd. 2 to the 2nd is as well. And 2 to the 1st. And 2 to the 0 is off. We add these together. There's 10 and 4 are 8. So that is 18. I get 78. And it does indeed look that's what I got when I ran that number. So 78 base 10 is equal to, well, we don't have to specify that number since it's leading. 1 0 0 1 1 1 0. Oh, I just killed it. There we go. And we'll do this last one. Okay, last one. So 2 to the 7th is off, 2 to the 6th is off. Let's do 32 for 2 to the 5th, 32. 16 is on, 8 is on, 0 is off. Sorry, 2 to the 2nd is off. 2 to the 1 is on. 2 to the 0 is on. We add 10 there, 10 there, and a 1. That should be 21. I wrote 18. Why did I write 18? That's supposed to be 16. Let's fix this problem. Sorry. 16, 8, 2, and 1. One more time with feeling this time, of course. So 8 gives me 10. 6, 7, 8, 9. That's 9. 9 plus 10 is 19. 3, 4, 5. 59. That looks significantly better than what I was going for a second ago. So 59 base 10 is indeed 111011 in binary. So to wrap up, why do you want to learn this? Well, apart from the fact that digital computers are based on the binary numbering system, if you ever want to do IP version 4 addressing, such as subnetting, then you have to know how to do binary. Now, I do realize that there are tons of tools and other things available now to do these calculations for you. It's always a good idea for job interviews if they hand you a piece of paper and say, here's an IP address, can you subnet this so that there are that there are 4 subnets, for example. You're definitely going to want to know how to break that down in binary. Of course, you also could probably figure out that, assuming that those 4 subnets total and not usables, then of course .64 will do that for you. But, or I shouldn't say .64. The ranges will start at 64, 128, 192, and of course 0. But anyways, so it's always a good idea to learn how to do this yourself, just in case of those pesky interview questions where they're actually seeing whether or not you can actually do what you're talking about. So again, to do binary to decimal, the first thing you're going to want to do is to write out 128, 64, 32, 16, 8, 4, 2, and 1. And if you can't remember that, just remember, since it's binary, 2 to the 0th, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6, and 2 to the 7. And if you do these calculations, you get these values. So whichever one is easier to remember, that's all you have to do. There is, of course, another way that I'll talk about in a future video. With that, I'm going to bring this video to an end. If you have any questions, feel free to leave them in the comments below. And I hope you have a great rest of the day.